Welcome to the ET380 lecture video for tuned circuits and resonance. Let's look at tuned circuits and resonance. And the first thing we need to go back and review capacitive reactance. So capacitive reactance is 1 over 2 pi Fc, frequency and capacitance. So as frequency increases, the reactance decreases. Let's look at inductive reactance. So inductive reactance equals 2 pi FL, frequency and inductance. And as frequency increases, the reactance increases. Let's take a look at series resonance. Here we have an impedance versus frequency chart, and we have the positive inductive reactance and our capacitive reactance. And our resonant frequency, F of R, is where X of L equals X of C. So here, when the two are equal, we have our resonant frequency. So X of L and X of C cancel. So impedance at the resonance is only the resistance in the wire. Gain is therefore high at resonance. Other frequencies above and below are opposed by X of L and X of C. Here I'm showing a gain versus frequency, and what happens is it becomes a band pass filter at resonance. Here's an example of a real-world series resonance problem. And here we have an antenna and our series resonant circuit and a high-frequency receiver. So we're trying to listen to a radio station in Australia, but the local stations nearby override the weak Australian. And we want to block those out. So we go ahead and we design this circuit which blocks all of our noisy circuit so we can listen to our Australian music. Okay, let's take a look at parallel resonance. Here's our parallel circuit of an inductor and capacitor. And if we look at our plot of impedance versus frequency, we have our inductive reactance, X of L, and our capacitive reactance, X of C. Where they are equal is our resonant frequency, F of R. So X of L equals X of C at resonance. Frequencies below resonance pass through a lower XL. Frequency above resonance pass through a lower XC. Impedance is high at resonance. At parallel resonance, we form a band reject filter at that frequency. So at that point, we reject that frequency. Here's a real-world example of parallel resonance. We have 3 strong local stations and 4 weaker ones. And we want to build this circuit, a resonant circuit. It's parallel. And what it allows us to do is block some of the stronger stations and allow the other weaker ones to be received.